Long before cities rose and farms spread across the land, before history was written and kings ruled empires, Earth was locked in the grip of ice, a frozen world where glaciers crushed mountains, megafauna roamed grasslands that stretched beyond horizons, and humans lived not as masters, but as survivors clinging to warmth in a landscape designed to kill them. This wasn't some distant alien planet. This was home, transformed into something so extreme, so brutal, and so magnificent that it seems pulled from myth rather than memory. The last ice age was Earth's final dress rehearsal before the modern world, a time when evolution tested its most spectacular creations one last time before stripping them away forever. Giant sloths browsed forests that would vanish. Saber-toothed cats stalked prey that would go extinct. Woolly mammoths crossed land bridges that would sink beneath rising seas. This is the story of Earth during its coldest chapter, when ice ruled half the planet and life adapted, thrived, and ultimately faced an apocalypse that would reshape everything. The ice sheets descend. Ice doesn't just fall from the sky and pile up into glaciers kilometers thick. It grows, slowly, relentlessly, year after year, century after century, compressing under its own weight until it becomes a living force that grinds continents into dust and carves valleys where none existed before. The ice sheets that defined the last glacial maximum weren't random. They were the result of planetary mechanics operating on scales humans can barely comprehend, driven by wobbles in Earth's orbit that shifted how sunlight struck the northern hemisphere. When summers grew too cool to melt winter's snow, ice began accumulating in northern Canada, Scandinavia, and Siberia. What started as snowfields transformed into domes of ice that spread outward like frozen floods, advancing at rates measured in meters per year, but unstoppable across millennia. The Laurentide ice sheet alone covered nearly all of Canada and extended deep into what is now the northern United States. At its peak, this single mass of ice was over 3 kilometers thick in places, heavy enough to press the Earth's crust downward, creating depressions that wouldn't rebound for thousands of years after the ice melted. The Cordilleran ice sheet mantled the Rocky Mountains and coastal ranges of western North America, merging with the Laurentide in some regions to form an unbroken wall of ice, stretching from the Pacific to the Atlantic. In Europe, the Fennoscandian ice sheet smothered Scandinavia, pushing south into Germany and Poland. Smaller ice caps crowned the Alps, the Pyrenees, and mountain ranges across Asia. These ice sheets weren't static monuments. They flowed like impossibly slow rivers, driven by gravity and the plastic deformation of ice under pressure. At their bases, meltwater lubricated movement, allowing glaciers to surge forward during cold periods and retreat during brief warm spells. The ice carried everything it touched: boulders, gravel, sand, soil, grinding bedrock into powder and depositing debris in massive moraines that marked the limits of glacial advance. Landscapes were erased and rewritten. River valleys became U-shaped troughs. Mountains were sharpened into horns and ridges. Lakes formed in depressions scoured by ice or dammed by glacial debris. The sheer volume of water locked in ice had profound effects. Sea levels dropped by over 120 meters, exposing continental shelves and creating land bridges that didn't exist before or since. The Bering Land Bridge connecting Asia and North America became a corridor for migration, not just for humans, but for horses, camels, mammoths, and countless other species moving between continents. The British Isles were connected to mainland Europe. Indonesia's islands merged into continuous landmasses. The Persian Gulf dried into a river valley. Coastlines moved outward by hundreds of kilometers, and what had been shallow seas became tundra, grassland, or desert. The ice also transformed atmospheric circulation. With so much of the northern hemisphere buried under reflective white ice, global temperatures plummeted. The temperature difference between equator and poles intensified. strengthening winds and altering storm tracks. Jet streams shifted southward, bringing cold, dry conditions to regions that are temperate today. Deserts expanded. Tropical rainforests shrank into isolated refugees. The Amazon basin, now Earth's largest rainforest, became fragmented patches of trees separated by grassland. But ice wasn't uniform in its dominance. Even at the coldest point, large regions remained ice-free. Central Alaska stayed relatively warm and dry, protected by mountains that block moisture from the Pacific. This created the mammoth steppe, a vast grassland ecosystem unlike anything existing today. Siberia's interior, though brutally cold, remained mostly unglaciated. Parts of the Yukon and Central Asia escaped the ice, serving as refuges where life persisted through the worst of the cold. The ice sheets also contain detailed records of Earth's climate. As snow fell and compressed into ice, it trapped air bubbles, dust, pollen, and volcanic ash, microscopic archives of atmospheric composition, temperature, and environmental conditions. Modern ice cores drilled from Greenland and Antarctica revealed that the last glacial maximum wasn't a single prolonged freeze, but a dynamic period punctuated by abrupt climate shifts. Temperatures could swing wildly within decades, driven by changes in ocean circulation, ice sheet dynamics, and greenhouse gas concentrations. These climate archives show carbon dioxide levels during the Ice Age dropped to around 190 parts per million, far below today's levels, and low enough to starve some plants of the gas they need for photosynthesis. Methane levels also plummeted, indicating reduced wetland activity and fewer large herbivores producing digestive gases. The atmosphere was drier, dustier, and filled with particles scoured from exposed continental shelves and deserts. This dust fertilized oceans, triggering plankton blooms that sucked carbon from the atmosphere and accelerated cooling in a feedback loop. Yet even in this frozen world, life found ways to survive. Ice sheets were barriers, but they were also architects of new habitats. Glacial meltwater-fed rivers that carved channels through permafrost. Winds deposited nutrient-rich dust across periglacial zones, creating fertile soils. And in the lands beyond the ice, evolution was working overtime, crafting creatures perfectly adapted to cold, scarcity, and survival at the edge of the possible. The mammoth steppe. Between the glaciers of the north and the temperate forests of the south stretched the mammoth steppe, a grassland ecosystem so vast, so rich in life, and so unlike anything that exists today that it seems more legend than fact. This wasn't the African savanna transplanted north. It wasn't the Great Plains of North America or the steppes of Mongolia. It was something unique, a cold, adapted grassland that supported herds of megafauna in densities rivaling modern African ecosystems. The mammoth steppe covered millions of square kilometers across Eurasia and North America, thriving in conditions that should have been hostile to large animals, but instead fostered one of the most spectacular assemblages of mammals Earth has ever seen. The foundation of this ecosystem was grass, not the lush green grass of summer meadows, but tough, cold-resistant species adapted to freezing temperatures, low moisture, and nutrient-poor soils. These grasses grew in dense mats that trapped heat near the ground, creating microclimates warmer than the frigid air above. They produced high-protein seeds and shoots that remained accessible even under snow. Their roots stabilized soil and prevented erosion, building organic layers that enriched the ground over millennia. This vegetation wasn't just food, it was infrastructure, creating habitat complexity that supported rodents, birds, insects, and the massive herbivores that defined the steppe. Woolly mammoths were the architects of this landscape. Standing over 3 meters tall and weighing up to 6 tons, these giants moved across the steppe in herds, grazing on grasses, sedges, and shrubs. Their curved tusks weren't just for display, they were tools for sweeping snow aside to reach vegetation, stripping bark from trees, and defending against predators. Their trunks could pluck individual grass blades or uproot entire shrubs. Mammoth teeth were marvels of evolutionary engineering, with multiple grinding plates that wore down and were replaced continuously throughout life, allowing them to process enormous quantities of tough, fibrous vegetation. But mammoths weren't alone. Woolly rhinoceroses, stocky, two-horned herbivores covered in shaggy fur, shared the steppe, using their front horns to scrape away snow and access buried plants. These animals were built like living battering rams, with thick skulls and powerful neck muscles that allowed them to push through snowdrifts and defend against predators. Their fossils show they thrived across Eurasia, occupying habitats from cold steppes to periglacial tundra. Giant ground sloths lumbered across North and South American grasslands, some species reaching the size of elephants. Unlike their small tree-dwelling descendants, these sloths were terrestrial giants with massive claws used for stripping branches and digging up roots. Their slow metabolism allowed them to survive on low-quality vegetation, and their size protected them from most predators. Some species, like Megatherium, stood on hind legs to reach high branches, using their weight to topple trees and feed on leaves inaccessible to other herbivores. Bison dominated the steppe in North America, but these weren't the relatively small bison seen today. Steppe bison, ancestors of modern bison, were larger, with horns spanning over 2 meters. They migrated in vast herds, following seasonal vegetation growth and creating trails that became geological features. Their grazing maintained grasslands by preventing shrub encroachment, recycling nutrients through dung, and creating disturbances that promoted plant diversity. Wild horses, ancestors of domestic horses, galloped across Eurasian and American steppes in herds numbering thousands. These weren't the tall, graceful horses of modern imagination. Ice Age horses were stocky, with thick coats, powerful legs, and adaptations for endurance running in cold climates. They grazed year-round, pouring through snow to reach dried grasses, and their movements helped distribute seeds across vast distances. Musk oxen, perfectly adapted to Arctic conditions, formed defensive circles when threatened, using their horned heads and thick skulls to protect calves from predators. Their undercoat, kiviat, was 8 times warmer than sheep's wool, providing insulation in temperatures that dropped below -50 degrees Celsius. These animals survived where others couldn't, thriving on marginal vegetation and enduring storms that killed less adapted species. The steppe also supported smaller herbivores that played crucial ecological roles. Saiga antelope, with their bizarre bulbous noses that warmed frigid air before it reached lungs, migrated across Eurasian grasslands in herds. Arctic ground squirrels hibernated through brutal winters, their body temperatures dropping to sub-zero levels, one of the few mammals capable of surviving frozen tissues. Lemmings, voles, and pikas lived in vast colonies, their burrows aerating soil and their grazing preventing moss dominance that would have smothered grasslands. What made the mammoth steppe so productive wasn't just the herbivores, but the dynamic interaction between animals, plants, and climate. Large herbivores prevented shrub and tree encroachment, maintaining open grasslands that reflected less sunlight than forests and stayed cooler. Their trampling broke up insulating moss layers, allowing permafrost to persist even during warmer periods. Their dung fertilized soils, supporting diverse plant communities. This wasn't passive grazing, it was ecosystem engineering on a continental scale. The steppe's productivity also resulted from nutrient cycling enhanced by glacial processes. Wind-blown dust from exposed continental shelves, glacial outwash, and eroded mountains deposited minerals across the landscape, enriching soils and supporting plant growth. Rivers draining glaciers carried sediment loads that fertilized floodplains. Even the cold helped. Freezing and thawing broke rocks into smaller particles, releasing nutrients and creating soils faster than in warmer climates. But this ecosystem existed on a knife's edge. The mammoth steppe required cold, dry conditions that suppressed tree growth while maintaining enough moisture for grasses. It needed large herbivores to maintain vegetation structure. It depended on stable climate patterns that kept winters cold but summers warm enough for plant growth. When any of these factors shifted, the entire system became vulnerable, and the shift they did catastrophically, irreversibly, and soon. Predators of the ice. Where massive herbivores grazed, apex predators followed, and the Ice Age produced some of the most spectacular carnivores ever to walk the earth. These weren't just bigger versions of modern predators, they were evolutionary experiments in killing efficiency, built for a world where prey animals weighed tons, and survival meant perfecting the art of the hunt in sub-zero temperatures. From saber-toothed cats to giant short-faced bears, Ice Age predators combined power, speed, and specialized weaponry in ways that would never be repeated after the ice melted and the megafauna vanished. Smilodon, the saber-toothed cat, is perhaps the most iconic Ice Age predator, but saber-toothed cat is misleading because it suggests a simple enlargement of canine teeth. Smilodon's adaptations went far deeper. Its canines were flattened, knife-like blades up to 28 centimeters long, serrated along the edges, and fragile enough that a direct impact against bone could shatter them. This meant Smilodon couldn't bite like modern big cats. Instead, it hunted using precision strikes to soft tissue, the throat, belly, or major blood vessels, delivered with a jaw gape exceeding 90 degrees, far wider than any living cat. Smilodon's body was built to immobilize prey before delivering the killing bite. Its forelimbs were massively muscled, with retractable claws used to grapple and pin struggling victims. Its shoulders and neck were extraordinarily powerful, providing the strength needed to hold down animals far larger than itself. Fossil evidence shows Smilodon frequently targeted young mammoths, bison, horses, and ground sloths, prey that could easily kill a careless predator. The abundance of healed injuries in Smilodon fossils suggests these cats lived dangerously, sustaining broken bones and deep wounds that healed because they lived in social groups that cared for injured members. The American lion, Panthera atrox, was the largest cat in the Western Hemisphere, 25% larger than modern African lions and possibly the largest feliid ever to exist. Unlike Smilodon's specialized killing method, the American lion relied on suffocation, clamping powerful jaws around the throat or muzzle of prey until it asphyxiated. Its size allowed it to tackle the largest herbivores on the continent, and its social structure, possibly living in prides like modern lions, gave it advantages in bringing down dangerous prey. Fossil sites show American lions and Smilodon sometimes competed for the same prey, leading to occasional fatal encounters between apex predators. In South America, Smilodon population grew even larger than its North American relatives, with some individuals reaching 300 kilograms. These giants roamed grasslands and forests, hunting massive ground sloths, toxodons, and early llama relatives. Their presence shaped entire ecosystems, keeping herbivore populations in check and preventing overgrazing that would have degraded vegetation. But felids weren't the only apex predators. The short-faced bear, Arctodus simus, was a nightmare made of flesh, standing over 3 meters tall on hind legs and weighing up to 900 kilograms. This wasn't a lumbering omnivore like modern bears. Arctodus had long, powerful limbs built for running, not climbing. Its skull was shortened and reinforced, suggesting bone-crushing bite forces. Its teeth showed wear patterns indicating a carnivorous diet, not the mixed omnivory of living bears. Some paleontologists believe Arctodus was primarily a scavenger, using its size and speed to intimidate other predators away from kills. Others argue it was an active hunter capable of chasing down prey across open terrain. Regardless of its exact hunting strategy, Arctodus was dominant. Fossil evidence shows it ranged across North America, from Alaska to Mexico, occupying habitats from grasslands to woodlands. Its presence may have shaped human migration patterns, as early humans entering the Americas would have competed with and fled from these enormous bears. Only when Arctodus went extinct did humans fully colonize southern regions of the continent. Dire wolves, canis de rus, hunted in packs across North and South America, targeting herbivores in coordinated attacks. Slightly larger and more robust than modern grey wolves, dire wolves had more massive skulls and teeth adapted for crushing bone. They were built for endurance hunting, chasing prey over long distances until exhaustion made it vulnerable. Fossil sites like the La Brea tar pits in California show dire wolves died in massive numbers, trapped while trying to scavenge or hunt animals stuck in asphalt seeps. The abundance of dire wolf fossils, thousands of individuals from a single site, suggests they lived in large packs and competed intensely for food. Cave lions, Panthera spelaea, stalked Eurasia, preying on reindeer, bison and horses. Slightly smaller than American lions, but equally formidable, cave lions left their mark not just in fossils, but in human art. Cave paintings from France and Spain depict lions in stunning detail, showing they coexisted with and terrified early humans. These paintings reveal that cave lions lacked manes, an adaptation that makes sense in cold climates where thick neck fur would have been a liability during hunts. The scimitar cat, Homotherium, took a different approach to saber-toothed predation. Its canines were shorter and less fragile than Smilodon's, allowing it to target different prey and use different killing techniques. Homotherium had longer legs and a more cursorial build, suggesting it hunted in open terrain, possibly pursuing prey over longer distances before delivering slashing bites. Fossil evidence from Texas shows Homotherium preyed heavily on young mammoths, dragging carcasses into caves where dozens of individuals fed communally. Smaller predators filled ecological niches that mega-carnivores couldn't exploit. Dholes, wild dogs of Asia, hunted in packs, using cooperation to bring down prey much larger than themselves. Wolverines scavenged and hunted small mammals, their tenacity and strength legendary, even among Ice Age fauna. Lynxes stalked forests and tundra edges, preying on hares and ground-nesting birds. Raptors also played crucial roles. Teratorns, enormous vulture-like birds, soared over grasslands, scavenging megafauna carcasses. With wingspans exceeding 5 meters, these birds could spot carrion from vast distances and descend to feed before mammalian scavengers arrived. Some species may have been active hunters, using size and powerful beaks to kill prey directly. What united Ice Age predators wasn't just their size, but their specialization. Evolution had honed each species to exploit specific prey, hunting strategies, and habitats. This specialization made them supremely effective, but also vulnerable. When prey populations shifted or disappeared, predators couldn't adapt quickly enough. The very traits that made them dominant, massive size, specialized weapons, narrow dietary niches, became liabilities when ecosystems collapsed. The age of ice was also the age of super predators, and when the ice retreated, these killers had nowhere left to hunt. Humans enter the stage. In a world dominated by creatures that could crush bone with single bites, outweigh humans 20 to 1, and survive temperatures that would kill naked apes within hours, one species did something unprecedented. It not only survived, but began spreading across every habitable continent on Earth. Humans during the Ice Age weren't the masters of their environment. They were clever, adaptable opportunists who turned biological weaknesses into technological strengths, transforming themselves from vulnerable primates into the most dangerous predators the planet had ever seen. Their arrival marked a turning point in Earth's history, one that would ultimately reshape ecosystems and drive the first wave of extinctions directly caused by a single species. Modern humans, Homo sapiens, emerged in Africa and began spreading into Eurasia during periods when climate corridors opened. By the height of the last glacial maximum, humans occupied territories from southern Africa to northern Siberia, from Western Europe to Southeast Asia. They weren't alone. Neanderthals still inhabited Europe and Western Asia, cold-adapted hominins who had lived through multiple glacial cycles. Denisovans occupied parts of Asia, their genetics surviving in modern populations even though their fossils remain rare. Other archaic humans may have persisted in isolated pockets, but Homo sapiens possessed something unique, a combination of cognitive flexibility, social complexity, and technological innovation that allowed them to outcompete every other hominin species. Fire was humanity's first great weapon against the cold. Unlike Neanderthals, who used fire opportunistically, Homo sapiens controlled it completely. They could start fires in any weather, maintain them through storms, and transport embers across vast distances. Fire provided warmth, protection from predators, light during long polar nights, and a way to process food that would otherwise be indigestible. Cooking broke down tough plant fibers and killed parasites in meat, extracting more calories from limited resources. Fire also allowed humans to occupy caves and rock shelters, smoking out dangerous animals and creating semi-permanent settlements in regions where exposure would otherwise be fatal. Clothing was the second revolution. Humans lacked the thick fur of mammoths, the dense wool of musk oxen, or the insulating fat of seals. Instead, they invented artificial pelts, sewn garments made from animal hides, furs, and eventually woven plant fibers. Archaeological evidence shows tailored clothing appeared in northern regions during the worst cold periods, with carefully crafted boots, pants, parkas, and hoods that trapped body heat and shed moisture. Eyed needles made from bone allowed precise stitching, creating waterproof seams and fitted garments that moved with the body. This technology was so effective that humans could survive Arctic winters that killed every other large mammal without specialized physical adaptations. Shelter building advanced rapidly. Early humans constructed sophisticated dwellings from mammoth bones, tusks, and hides, creating domed structures that could house extended families through winter. One site in Ukraine preserves the remains of a dwelling built from the bones of over 90 mammoths, arranged into walls and covered with hides. These weren't temporary camps, they were engineered habitats that required planning, cooperation, and significant labor investment. Inside, hearths provided heat, and carefully designed smoke holes prevented suffocation while maintaining warmth. Tools evolved from simple stone flakes into specialized implements for every task. Humans crafted spear points, knives, scrapers, awls, and burins, each designed for specific functions. They developed atlatls, spear throwers that dramatically increased projectile velocity and range, allowing hunters to kill dangerous game from safer distances. They invented traps, snares, and nets, capturing prey without direct confrontation. They built boats and rafts, crossing rivers and coastlines to access isolated resources. They created art, carving figurines, painting caves, and producing the first musical instruments, innovations that strengthened social bonds and transmitted knowledge across generations. Language, fully modern, syntactically complex language, gave humans their greatest advantage. Unlike any other species, humans could share detailed information about animal behavior, weather patterns, resource locations, and hunting strategies. They could plan coordinated hunts involving dozens of individuals, assign roles, and execute complex tactics. They could teach skills to children too young to participate, ensuring knowledge transferred across generations. They could gossip, form alliances, detect cheaters, and enforce social norms that increased group cohesion. Language transformed humans from isolated individuals into superorganisms, capable of collective action far beyond their physical capabilities. Human hunting strategies were revolutionary. Rather than chasing prey like wolves or ambushing like cats, humans used endurance and intelligence. They tracked wounded animals for days, waiting for blood loss and infection to weaken them. They drove herds toward cliffs, marshes, or waiting hunters, causing stampedes that killed multiple animals simultaneously. They set grassland fires, channeling fleeing game into killing zones. They hunted during vulnerable periods, when animals gave birth, during storms, or when snow depth hindered movement. These strategies allowed small bands of humans to kill animals vastly larger and stronger than themselves. Archaeological evidence shows humans preyed on mammoths, mastodons, giant ground sloths, and other megafauna throughout their range. Butchery sites preserve stone tools alongside mammoth bones showing cut marks, evidence of systematic processing. In some regions, mammoth bone piles suggest humans killed far more than they could immediately consume, possibly storing meat in permafrost or returning seasonally to productive hunting grounds. This wasn't subsistence hunting, it was surplus killing, made possible by technology and cooperation. But humans weren't just hunters. They were collectors, scavengers, fishers, and opportunists. They harvested shellfish along coastlines, caught salmon during spawning runs, collected bird eggs, dug roots, and gathered nuts. They scavenged predator kills, using tools to access marrow and meat that other scavengers couldn't reach. This dietary flexibility allowed humans to survive in environments where specialists starved. Social organization became increasingly complex. Humans formed bands of related families, clans of multiple bands, and regional networks connected by trade, marriage, and shared ritual. They exchanged raw materials, high-quality stone, shells, ochre, amber, across distances exceeding hundreds of kilometers. They created symbolic objects that communicated group identity. They buried their dead with grave goods, suggesting belief systems that contemplated existence beyond death. They made art depicting animals, humans, and abstract symbols whose meanings remain mysterious but clearly held significance. Human cognition allowed them to model scenarios mentally, test ideas without physical trial, and innovate rapidly. When climate shifted, humans adapted their toolkits, hunting strategies, and settlement patterns within generations. When resources depleted, they moved or switched targets. When competition intensified, they cooperated more tightly or developed new technologies. This flexibility was unmatched in the natural world, yet humans were still vulnerable. Infant mortality was high. Injuries were common and often fatal. Starvation during bad years killed significant portions of populations. Predators occasionally killed humans, especially children. Climate shifts forced migrations or caused population crashes. But humans persisted, spreading into every available habitat and transforming themselves from one species among many into an ecological force comparable to climate itself. The frozen coasts. While glaciers crushed the interior and grasslands stretched across continental expanses, Earth's coastlines during the Ice Age were utterly transformed. Not just reshaped, but relocated, exposing vast plains where oceans now flow and creating temporary bridges between continents that would vanish forever when the ice melted. These frozen coasts weren't barren wastelands but rich ecotones where terrestrial and marine ecosystems collided, creating unique habitats that supported life found nowhere else. From exposed continental shelves teeming with megafauna to ice-choked Arctic shores where marine mammals hauled out in vast colonies, the coasts of the Ice Age were frontiers of biological productivity and human expansion. Sea levels had dropped so dramatically, more than 120 metres below present levels, that the ocean's edge stood far from where it does today. The English Channel was a river valley. The North Sea was a plain dotted with lakes and crossed by rivers. The Persian Gulf didn't exist as a body of water, but as a river system draining Mesopotamia. Between Australia and New Guinea stretched Sahul, a single landmass that modern humans colonised over 50,000 years ago. Sundarland connected the islands of Indonesia into a vast peninsula, providing migration routes for elephants, tigers and orangutans. The most significant of these exposed lands was Beringia, the landmass connecting Siberia and Alaska across what is now the Bering Strait. Beringia wasn't merely a narrow bridge, but a subcontinent spanning over 1,600 kilometres from north to south, covered in tundra and grassland that supported mammoths, horses, bison and lions. This landscape remained ice-free throughout the glacial maximum, serving as a refuge where species that couldn't survive further south persisted. Beringia was also the gateway humans used to enter the Americas, crossing from Asia in multiple waves and spreading southward once ice sheets, retreating open corridors. These newly exposed coastlines weren't immediately habitable. Permafrost locked much of the ground, and fierce winds swept across open plains with nothing to block them. But over centuries, vegetation colonised these spaces. Grasses, sedges and low shrubs took root in thin soils. Lichens and mosses covered rocks. Seasonal meltwater created wetlands and shallow lakes that attracted waterfowl. Slowly, ecosystems established themselves on lands that had been underwater for tens of thousands of years. Marine life adapted to colder, more productive oceans. The drop in sea level concentrated nutrients in smaller ocean basins, and glacial meltwater carried minerals from eroded rock into coastal waters. Upwelling zones became supercharged, driving plankton blooms that fed fish, which fed seabirds, seals, and whales. Cold water species like cod, herring, and caplin thrived in numbers impossible to imagine today. Kelp forests grew in shallow waters, providing habitat for invertebrates, fish, and sea otters. Pinnipeds, seals, sea lions, and walruses colonised ice-choked coasts in massive numbers. Walruses hauled out on beaches in herds numbering thousands, their tusks used to rake seafloor sediments for clams and mussels. Elephant seals bred on isolated beaches, males fighting brutal battles for breeding rights. Harbour seals gave birth on ice floes, their pups growing rapidly on fat, rich milk before learning to hunt fish. These marine mammals were crucial prey for coastal predators and human hunters, providing meat, fat and skins in environments where terrestrial resources were scarce. Polar bears roamed sea ice margins, hunting seals with patience and power. Unlike modern polar bears restricted to shrinking Arctic ice, Ice Age polar bears had vast expanses of stable ice platforms and abundant prey. They were larger than modern individuals, with broader skulls and more robust builds. Fossil evidence shows they ranged as far south as Britain and France during the coldest periods. Following sea ice that extended far beyond its current range, whales also adapted to Ice Age oceans, though their fossils are rare and their biology remains poorly understood. Baleen whales likely followed seasonal productivity pulses, migrating to high-latitude feeding grounds during brief summers. Toothed whales hunted fish and squid in deeper waters. Some species may have penetrated further into ice-covered seas than modern whales can, exploiting rich feeding grounds accessible only during the coldest periods. Seabirds nested on cliffs and islands in staggering numbers. Auks, puffins, guillemots, and kittiwakes formed colonies that blackened cliffsides and filled the air with calls. These birds fed on fish concentrated in cold, nutrient-rich waters, converting marine productivity into forms accessible to terrestrial predators. Gulls, terns, and skuas scavenged along shorelines, cleaning beaches of carrion and stealing food from other birds. Coastal environments also supported unique terrestrial fauna. Muskoxen graze tundra vegetation near shorelines, their thick coats protecting them from Arctic storms. Reindeer migrated along coasts, feeding on lichens exposed by windblown snow. Arctic foxes scavenged seal carcasses and raided seabird colonies. Wolves patrolled beaches, hunting marine mammals and terrestrial prey opportunistically. Humans discovered these coastal resources early and exploited them intensively. Shell middens, massive piles of discarded shells, bones and tools, mark ancient coastal settlements from Europe to Asia to the Americas. These sites show humans harvested shellfish, caught fish with nets and hooks, hunted seals and seabirds, and collected seaweed. Coastal resources were predictable and abundant, allowing human populations to grow larger and settlements to become more permanent. The exposed continental shelves also preserved evidence of human habitation, now submerged beneath modern seas. Doggerland, the North Sea plain, was home to Mesolithic cultures for thousands of years before rising seas flooded it. Fishermen occasionally dredge up stone tools, mammoth bones, and even human artifacts from the seafloor, evidence of lost landscapes and forgotten peoples. Similar drowned sites exist off the coasts of Southeast Asia, Australia, and the Americas, representing entire chapters of human history erased by post-glacial sea level rise. But these coasts were temporary. As the ice began melting, seas rose rapidly, sometimes meters per decade, during pulses of catastrophic ice sheet collapse. Coastlines retreated inland, drowning plains, flooding river valleys, and severing land bridges. Species that depended on these habitats had to migrate or perish. Humans abandoned settlements and moved inland, losing access to productive coastal zones. Within a few thousand years, the Ice Age coastlines vanished completely, leaving only subtle geological traces and submerged archaeological sites that hint at their former richness. Europe under ice. Europe during the last glacial maximum was split into two worlds, a frozen north buried under ice sheets extending from Scandinavia to the British Isles, and a cold but habitable south where glaciers clung to mountains but left valleys and plains open to life. This division created one of the most dynamic regions on Earth, where species compressed into narrow refuges, human cultures flourished in challenging conditions, and evolution accelerated as populations fragmented and adapted to local environments. The Europe of the Ice Age bore almost no resemblance to the continent we know today, transformed into a patchwork of tundra, steppe, and isolated forests, where survival demanded constant innovation. The Fennoscandian ice sheet smothered Scandinavia under ice over 3 kilometers thick, grinding mountains into rounded domes and carving fjords that would later fill with seawater. This ice extended south into northern Germany and Poland, pushing the habitable zone toward the Mediterranean. Britain was connected to the continent, its southern regions covered in tundra, grazed by reindeer, horses, and woolly rhinoceroses. Ireland remained ice-free in parts but was isolated by glaciers, limiting species colonization. South of the ice, conditions varied dramatically. The Alps were crowned with their own ice cap, with glaciers flowing down valleys and joining in some areas to form ice fields. The Pyrenees, Carpathians, and other mountain ranges supported local glaciers. But between these frozen highlands stretch periglacial zones, cold steppes and tundra, where permafrost locked the ground, but vegetation still grew during brief summers. These regions supported surprising biodiversity, with megafauna concentrating in valleys that offered shelter from wind and access to water. Mammoth bones found across Central Europe show these giants roamed from France to Ukraine, following seasonal vegetation growth. They gathered near rivers where willows and shrubs provided browse during winter, then moved to open grasslands in summer. Cave paintings from France and Spain depict mammoths with extraordinary accuracy, showing humans not only hunted these animals, but observed them closely enough to capture details of posture, hair patterns, and behaviour. The iconic woolly rhinoceros inhabited European steppes in large numbers, its fossils common from Britain to Siberia. These massive herbivores used their horns to clear snow and access buried vegetation, creating feeding craters that other species exploited. Their thick fur and compact bodies conserved heat, and their nasal cavities were adapted to warm, frigid air before it reached their lungs. Despite their fearsome appearance, they were primarily peaceful grazers, though capable of deadly defence when threatened. Cave bears, Ursus spelaeus, were the giants of European mountains and forests, though they weren't primarily predators. Larger than modern brown bears and built with massive skulls and powerful limbs, cave bears were primarily herbivorous or omnivorous, feeding on plants, roots, and occasional carrion. They hibernated in caves during winter, and thousands died in their dens, leaving rich fossil deposits. Some caves contain the remains of hundreds of individuals, accumulated over millennia. Humans sometimes competed with cave bears for cave space, and evidence suggests occasional conflicts when bears refused to vacate shelters humans wanted to occupy. Cave lions prowled European grasslands and forests, hunting horses, bison, and reindeer. These formidable predators lived alongside Neanderthals and early modern humans, shaping settlement patterns and hunting strategies. The famous paintings in Chauvet Cave depict cave lions in remarkable detail, showing pride dynamics and hunting behaviour that reveals intimate knowledge of these predators. Giant deer, megaloceros, roamed Ireland, Britain and continental Europe, sporting antlers that could span 3.5 metres, the largest antlers of any deer species ever. These weren't just display structures, they were weapons used in combat between males during mating season. The energetic cost of growing such massive antlers each year was immense, requiring rich feeding grounds and good health. Their extinction may have resulted from habitat loss as forests replaced open grasslands, making their enormous antlers a liability in dense vegetation. Humans in Ice Age Europe developed sophisticated cultures adapted to extreme conditions. Neanderthals had occupied the continent for hundreds of thousands of years, perfecting cold weather survival strategies. They built shelters, controlled fire, crafted specialized tools, and hunted large game cooperatively. They buried their dead, cared for injured individuals, and possibly possessed language. But as modern humans entered Europe around 40,000 years ago, Neanderthal populations began declining. Whether through competition, interbreeding, disease, or climate stress, Neanderthals disappeared from Europe around 40,000 years before present, leaving only their genes in modern human genomes. Modern humans who replaced them brought revolutionary technologies. They created blade tools, long, thin stone flakes that maximized cutting edge from limited raw material. They developed standardized tool types for specific tasks. They invented throwing spears with detachable points, allowing hunters to carry multiple projectiles. They made jewelry, figurines, and cave art that marked the emergence of symbolic thought and complex culture. European cave art from this period is among the most spectacular in the world. Lascaux, Altamira, Chauvet, and dozens of other sites preserve vivid paintings of horses, bison, aurochs, mammoths, rhinoceroses, lions, and humans. These weren't crude stick figures, but anatomically accurate depictions showing movement, perspective, and intimate knowledge of animal behavior. Some paintings were placed deep in cave systems, requiring dangerous journeys into total darkness, suggesting they held ritual or spiritual significance beyond mere decoration. Humans also created portable art, carved figurines, engraved bones, and decorated tools. The Venus figurines, stylized female forms emphasizing fertility attributes, appear across Europe, suggesting shared symbolic systems or religious beliefs. Musical instruments, including bone flutes, demonstrate artistic expression beyond visual art. These cultural innovations allowed humans to thrive in Ice Age Europe despite formidable challenges. They hunted megafauna, fished salmon runs, collected plants, and exploited every available resource. They formed regional groups with distinct tool styles and artistic traditions, suggesting cultural diversity and social complexity. They traded materials across hundreds of kilometers, creating networks that connected disparate populations. But survival wasn't guaranteed. Climate fluctuations caused repeated population crashes. Harsh winters killed vulnerable individuals. Food shortages during bad years forced migrations or led to starvation. Predators occasionally killed humans. Injuries were common and often fatal. Yet humans persisted, adapting continually to shifting conditions. As the ice began retreating around 15,000 years ago, Europe transformed rapidly. Tundra gave way to shrublands, then forests. Megafauna declined as their open habitat disappeared. Human cultures shifted from big game hunting to more diverse subsistence strategies. The Europe of the Ice Age vanished, replaced by a landscape and ecology that would eventually support agriculture, cities, and civilizations. Built unknowingly on the foundations laid by those who survived the frozen millennia. Asia's frozen heart. Across the vast interior of Asia, the Ice Age created landscapes so extreme, so empty, and so brutally cold that they seem uninhabitable. Yet life not only persisted, but thrived in forms specifically engineered for survival at the edge of biological possibility. While ice sheets crushed northern Europe and North America, much of Siberia remained ice-free, transformed into frozen grasslands where temperatures plummeted to depths that would kill modern mammals within hours. This paradox, ice-free but frozen, resulted from unique geography that blocked moisture but allowed cold to dominate, creating the coldest terrestrial environments Earth has ever known, while simultaneously supporting megafauna diversity rivaling Africa's modern savannas. The reason Siberia escaped glaciation despite its extreme cold lies in precipitation patterns. Mountain ranges blocked moisture from the Pacific, creating a rain shadow that starved the region of the snowfall needed to build glaciers. What little snow fell sublimated in dry winter air or melted during brief summers. The result was a hypercontinental climate, extremely cold winters, warm summers, and very low annual precipitation. Permafrost extended to depths exceeding 1,000 meters in places, locking the ground into permanent frost even while supporting seasonal vegetation above. This frozen ground created unique geological features. Massive ice wedges formed as water seeped into cracks and froze, expanding and creating polygonal patterns visible from space. Pingos, ice-cored hills, rose where groundwater froze and expanded under pressure. Thermokarst lakes formed when permafrost thawed locally, creating depressions that filled with meltwater. These features shaped drainage patterns, influenced vegetation distribution, and created microhabitats that increased ecosystem complexity. The mammoth steppe extended across Siberia in its fullest expression, covering millions of square kilometers, with grasslands richer and more productive than those existing anywhere today. This wasn't the sparse tundra of modern Arctic regions, but a dense, diverse plant community dominated by grasses, herbs, and dwarf shrubs. The secret to its productivity was the herbivores themselves: mammoths, rhinoceroses, horses, bison, and countless smaller species whose grazing, trampling, and fertilizing maintained the grassland against encroaching shrubs and moss. Woolly mammoths reached their greatest abundance in Siberia, with some regions supporting population densities comparable to modern African elephants. Their remains are so common that tusks and bones regularly wash out of riverbanks, and local people have collected mammoth ivory for centuries. Some frozen carcasses have been discovered with soft tissues, hair and even stomach contents preserved, providing unprecedented insights into mammoth biology. These finds show mammoths fed on grasses, sedges, willow shoots and flowers. A diverse diet requiring extensive daily grazing. The preservation of mammoth carcasses in Siberian permafrost sparked wild speculation for centuries, including claims that mammoths still lived in remote regions or could be resurrected from frozen tissue. While resurrection remains theoretical, the quality of preservation is remarkable. DNA has been extracted from multiple specimens, revealing mammoth genetics in detail and confirming their close relationship to modern elephants. Proteins, lipids, and even cellular structures sometimes survive, providing molecular evidence of adaptations to extreme cold. Woolly rhinoceroses were equally common, their fossils abundant from Western Europe to eastern Siberia. Unlike mammoths, which ranged across varied habitats, rhinoceroses seem to prefer drier, more open terrain. Their compact bodies and thick horns made them formidable despite being herbivores, and evidence suggests they defended feeding territories against competitors. Horses in Ice Age Siberia were smaller and stockier than modern breeds, with thick winter coats and adaptations for pawing through snow. They lived in large herds that migrated seasonally, following vegetation growth and avoiding deep snow. Modern Przewalski's horses, the only truly wild horses remaining, may be direct descendants of these Ice Age populations, though even they have been reduced to tiny numbers and survive only through conservation efforts. Bison, camels and Sager antelope added to the herbivore diversity. Yes, camels, not the humped desert specialists of today, but different species adapted to cold grasslands. Fossil evidence shows camels originated in North America, crossed Beringia into Asia, and survived there long after their American relatives went extinct. Ice Age camels likely lacked the pronounced humps of modern species, storing fat more evenly across their bodies as insulation. Predators in Siberia were equally impressive. Cave lions hunted across the region, their fossils common in permafrost deposits. One exceptional find from Siberia preserved a lion cub in permafrost so perfectly that its fur, whiskers, and internal organs remained intact, providing information about fur coloration, muscle structure, and diet impossible to obtain from bones alone. These frozen predators revealed that cave lions had pale fur without manes, adaptations for Arctic hunting. Wolves, Arctic foxes, and wolverines filled smaller predatory niches. Wolves hunted in packs, taking down horses, bison, and young mammoths. Arctic foxes scavenged kills and hunted lemmings, which existed in vast numbers. Wolverines, despite their small size, were fierce enough to drive larger predators from kills and survive on carrion through brutal winters. Humans entered Siberia surprisingly early, with archaeological evidence showing occupation dating back over 30,000 years. These weren't passive survivors, but active colonizers who developed technology specifically for Arctic life. They built substantial dwellings using mammoth bones and tusks as structural elements, with walls of packed earth and roofs covered in hides. Inside, central hearths provided heat, and careful design prevented smoke accumulation while maintaining warmth. These homes could shelter extended families through winters lasting 8 months. Siberian humans hunted mammoths, but probably not as frequently as popular culture suggests. More likely, they targeted horses, bison, and reindeer, while opportunistically scavenging mammoth carcasses. They fished through ice on frozen rivers and lakes. They collected bird eggs during brief summers. They stored food in permafrost, using natural freezing as refrigeration. Their technology included tailored clothing, sewn with sinew using bone needles, garments so effective that traditional Arctic peoples used similar designs into the 20th century. The Yana rhinoceros horn site in northeastern Siberia, one of the northernmost Ice Age human sites known, shows people living above the Arctic Circle during the coldest periods. They crafted tools from mammoth ivory and rhinoceros horn, materials requiring sophisticated carving techniques. They hunted reindeer and other game in near total darkness during winter months. Their survival in such extreme conditions demonstrates human adaptability at its most impressive. As the climate warmed and the Ice Age ended, Siberia transformed. Grasslands gave way to forests of larch, pine and birch. Permafrost thawed in many areas, creating vast wetlands. The megafauna declined rapidly, unable to adapt to changing vegetation and increased human hunting pressure. Mammoths disappeared from mainland Asia around 10,000 years ago, though isolated populations survived on Wrangel Island until 4,000 years ago, long after pyramids rose in Egypt. These final mammoths were dwarfed by their Ice Age ancestors, reduced by island effects to half their original size, eking out existence on a shrinking refuge before extinction claimed them too. Africa's surprising stability. While ice crushed the north and sea levels plummeted globally, Africa remained relatively stable, a bastion of continuity in a world convulsed by climate extremes. But stable doesn't mean unchanged. Africa during the Ice Age experienced profound transformations as rainfall patterns shifted, deserts expanded and contracted, forests fragmented into isolated refugees, and savannas shifted their boundaries by hundreds of kilometres. The animals that define Africa today, elephants, lions, zebras, giraffes, persisted through these changes, but they shared the landscape with megafauna that would later vanish and human populations that would eventually colonize every other continent. Africa's Ice Age story is one of resilience, adaptation, and the emergence of humanity itself. The Sahara Desert, now the world's largest hot desert, fluctuated dramatically between hyper-arid wasteland and relatively green savanna. During the coldest periods, when northern ice sheets locked away moisture, the Sahara expanded, pushing habitable zones toward the equator and fragmenting populations. But during interglacial warm periods and certain climate oscillations, monsoon patterns shifted northward, bringing rainfall to regions now barren. The Sahara temporarily transformed into grassland dotted with lakes, supporting hippos, crocodiles and human populations, whose rock art still decorates cliff faces in what are now desolate wastes. These fluctuations created evolutionary pressures on African species. Animals that could migrate between northern and southern regions survived. Those restricted to shrinking habitats faced extinction risks. Elephants, for instance, moved between forest and savanna as conditions changed, their flexible diet allowing exploitation of varied vegetation. Lions followed prey herds across shifting landscapes. Zebras and wildebeest adjusted migration routes. But some species couldn't adapt quickly enough. Africa's megafauna during the Ice Age included species no longer present. Giant buffalo, Pelorovis, roamed savannas with horns spanning over 2 meters, dwarfing modern Cape buffalo. These massive herbivores grazed in herds and used their size and weaponry to deter predators. Giant warthogs, oversized relatives of modern species, rooted for tubers and defended themselves with enlarged tusks. Enormous baboons climbed cliffs and lived in troops that intimidated even large predators. But Africa's most important Ice Age development was human evolution. While modern humans emerged in Africa over 300,000 years ago, the Ice Age saw their transformation from one hominin species among several to the sole survivors of the genus Homo. Climate fluctuations in Africa created alternating periods of connection and isolation between populations, driving rapid evolutionary change. Genetic evidence shows modern humans almost went extinct during the Ice Age, with populations crashing to just a few thousand individuals during particularly harsh periods. These bottlenecks left lasting marks on human genetics. Modern humans have remarkably low genetic diversity compared to other great apes, evidence of near-extinction events that eliminated most lineages. But the survivors possessed traits that would prove decisive: advanced cognitive abilities, complex language, sophisticated tool use, and social structures allowing cooperation at unprecedented scales. Around 70,000 years ago, modern humans began leaving Africa in waves that would eventually populate the entire world. These migrations weren't sudden exoduses, but gradual expansions following coastlines, river valleys, and game herds. Early groups crossed the Bab el-Mandeb Strait into Arabia, when low sea levels exposed shallow crossings. From there, they spread along the coasts of Asia, reaching Australia within 20,000 years. Other groups moved north through the Nile Valley into the Middle East, encountering Neanderthals, and eventually spreading into Europe and Asia. The timing of these migrations coincided with climate fluctuations that periodically made routes passable. During the wettest phases, when the Sahara greened, humans could cross regions now impassable. During coastal periods, low sea levels exposed beaches and plains that facilitated movement. Each wave of migration represented populations adapted to specific conditions, carrying distinct genetic signatures and cultural practices. Africa's Ice Age fauna also included modern species in forms slightly different from today. Elephants were somewhat larger, lions heavier, and certain antelopes more robust. These differences resulted from climatic stresses that favoured larger body sizes for heat retention and fat storage. As climates warmed and stabilised, many species trended towards smaller sizes, a pattern reversed from the usual evolutionary response to cooling. The continent's geographic diversity created numerous refugees where species survived harsh periods. Tropical rainforests of Central Africa contracted during cold, dry phases but never disappeared entirely, preserving gorillas, chimpanzees, and forest elephants. The Ethiopian highlands served as refuges for mountain-adapted species. Southern Africa's Cape region maintained unique flora and fauna isolated from changes further north. These refugees acted as evolutionary laboratories where populations diverged and sometimes gave rise to new species. Human impacts on African megafauna during the Ice Age were probably minimal compared to other continents. African animals had co-evolved with humans and early hominins for millions of years, developing instinctive wariness and defensive behaviours. Unlike naive fauna on other continents encountering humans for the first time, African animals knew how dangerous humans could be and adjusted behaviour accordingly. This may explain why Africa retained more megafauna diversity than any other continent, despite continuous human presence. Climate-driven habitat changes probably caused most African Ice Age extinctions. When forests fragmented, forest specialists went extinct. When savannas shifted, range-restricted species disappeared. When lakes dried, aquatic species vanished. But overall, Africa's extinctions were less severe than those on other continents. Evidence that gradual climate change allowed adaptation, while sudden shifts or naive prey populations led to catastrophe. As the Ice Age ended, Africa transitioned toward modern conditions earlier than most regions. The Sahara alternated between desert and savanna several more times before settling into its current hyper-arid state around 5,000 years ago. Forests expanded from their refuges, reconnecting populations. Savannas stabilized into the forms recognizable today. The megafauna that survived became the iconic African wildlife, familiar worldwide, a legacy of resilience through the most extreme climate fluctuations of the past 2 million years. The Americas before arrival. When humans first glimpsed the Americas from Beringia, they saw a landscape filled with animals beyond imagination. Creatures so massive, so strange, and so abundant that the continent seemed less a new world than a lost world where evolution had run wild in isolation. For millions of years, the Americas had developed unique fauna cut off from Eurasia and Africa, creating ecosystems unlike anywhere else on Earth. Giant ground sloths as large as elephants browsed forests from Alaska to Patagonia. Armadillo relatives the size of cars ambled across grasslands. Terror birds, flightless predatory birds standing taller than humans, stalked prey with serrated beaks. The Americas before human arrival were a megafaunal paradise that would soon face catastrophic transformation. North America's Ice Age fauna rivaled Africa's modern diversity. Columbian mammoths, slightly larger than their woolly cousins, range from Canada to Mexico, their fossils common in tar pits, riverbeds, and ancient sinkholes. These mammoths preferred temperate climates and open woodlands, browsing on trees and shrubs rather than grasses. Their tusks, sometimes exceeding 4 meters, were used for stripping bark, digging, and combat. American mastodons occupied forests and wetlands, their conical teeth adapted for browsing rather than grazing. Shorter and stockier than mammoths, mastodons had straighter tusks and more compact bodies suited for pushing through dense vegetation. They range from Alaska to Florida, leaving fossils in bog deposits where they got trapped while feeding. One site in Florida preserved a mastodon kill site where stone tools lay among butchered bones, direct evidence of human hunting. Giant ground sloths, several species collectively called megalonyx, megatherium, and nothrotheriops, were among the strangest American megafauna. Unlike small tree sloths of today, these giants walked on all fours, had massive claws, and reached weights exceeding 4 tons in the largest species. They reared on hind legs to reach high branches, using weight to topple trees and feed on foliage. Their slow metabolism allowed survival on low-quality browse, and their size protected them from most predators. Some ground sloths lived in caves, their dried dung preserved in arid caves of the southwest, containing pollen and plant remains that reveal Ice Age vegetation in remarkable detail. Glyptodonts, relatives of armadillos, looked like living tanks, covered in fused bony shells and sporting club tails. Some species grew 3 meters long and weighed over a ton. Their armor provided excellent protection, but limited mobility and speed. They grazed on grasses and low vegetation, relying on armor rather than flight when threatened. Their fossils are common across South and North America, evidence of a successful evolutionary strategy that lasted millions of years. Short-faced bears, Arctodus simus, were the largest mammalian land predators in North America, capable of reaching speeds over 50 kilometers per hour, despite weighing nearly a ton. Their long legs and shortened faces gave them a distinctive appearance, and their size allowed them to dominate any carcass through intimidation. Whether active hunters or specialized scavengers remain debated, but their presence shaped ecosystems, keeping other predators cautious and prey animals alert. Saber-toothed cats, including Smilodon fatalis, thrived in North America, with the La Brea tar pits in California preserving thousands of individuals. These weren't just random accumulations. Predators came to feed on trapped herbivores and became trapped themselves, creating fossil assemblages dominated by carnivores. The abundance of saber-tooths shows they were successful, possibly social hunters working cooperatively to bring down massive prey. American lions, dire wolves, and American cheetahs added to predator diversity. Yes, cheetahs, not as fast as African cheetahs, but built for pursuit across grasslands, chasing pronghorn antelope that evolved speed to escape these predators. Modern pronghorns still run faster than any existing North American predator, an evolutionary anachronism shaped by dangers that no longer exist. South America's fauna was even more bizarre, shaped by tens of millions of years of isolation before the Isthmus of Panama connected it to North America. When the continents joined around 3 million years ago, the great American biotic interchange occurred. Species flowed both directions, competing and sometimes driving native forms extinct. Toxodon, a massive, hippo-like mammal, wallowed in rivers and grazed wetland vegetation. Macrauchenia, a long-necked herbivore with a trunk, browsed trees and shrubs, its bizarre appearance combining features of llamas, horses and tapirs into something unlike anything alive. These native South American ungulates faced new competition from invading horses, deer and camels from North America. Terrorbirds, Forus racids, were apex predators in South America for millions of years. Standing over 2 meters tall with massive skulls and hooked beaks, they chased down prey using powerful legs and killed them with crushing bites. Though in decline by the Ice Age's peak, they persisted in some regions, overlapping briefly with humans who entered South America. Imagine encountering a predatory bird taller than yourself with a beak capable of crushing bones. Terrorbirds justified their name. Giant anteaters, capybaras the size of bears, and massive caimans filled ecological niches across South America. Forests, grasslands, wetlands and mountains each supported distinct communities. The Andes hosted unique high-altitude fauna, while the Amazon, though smaller and more fragmented than today, maintained tropical diversity. This was the Americas as humans found them, a megafaunal wonderland where evolution had produced forms rivaling anything from science fiction. Humans entering this realm were technologically sophisticated hunters who had refined their skills over tens of thousands of years in Eurasia. They faced prey animals with no instinctive fear of human weapons or tactics. The stage was set for one of the most dramatic ecological transformations in Earth's history, one that would empty the Americas of most large animals within just a few thousand years. Australia's ancient giants. When humans reached Australia over 65,000 years ago, they entered the most isolated and bizarre ecosystem on Earth, a continent where marsupials had evolved to fill every niche occupied elsewhere by placental mammals, where reptiles grew to monstrous sizes, and where birds became apex predators. Australia's Ice Age megafauna were products of tens of millions of years of evolution in complete isolation, creating species so unique that early European naturalists thought fossils were hoaxes or mistakes. These weren't just big versions of familiar animals. They were fundamentally different, shaped by environments and evolutionary pressures found nowhere else. The marsupial lion, Thylacoleo carnifex, was one of the most specialized predators ever to evolve. About the size of a modern leopard, but built more powerfully, Thylacoleo had the strongest bite force relative to body size of any mammal ever measured. Its teeth were completely unique, massively enlarged in sizes for stabbing and blade-like premolars for slicing, essentially turning its entire mouth into a pair of biological scissors. It likely ambushed prey from trees or rocks, using enlarged claws and crushing bites to kill animals much larger than itself. Fossil evidence shows Thylacoleo preyed on giant wombats, kangaroos and other megafauna, carving out a niche unmatched by any living predator. Diprotodon, the largest marsupial ever, was a rhino-sized wombat relative that grazed across Australian grasslands and woodlands. Weighing over 2 tons and standing 2 meters tall, Diprotodon travelled in herds, leaving footprint trackways preserved in clay pans and lake shores. Their fossils are common across Australia, often found in dried lake beds where entire herds perish during droughts. These gentle giants had no natural defences beyond size, making them vulnerable once humans arrived with sophisticated hunting techniques. Giant short-faced kangaroos, Procoptodon, stood over 2 meters tall and weighed twice as much as modern red kangaroos. Unlike their living relatives that hop efficiently, Procoptodon may have walked more often, using their massive size for reaching high branches. Their forward-facing eyes suggest better depth perception, possibly for navigating dense vegetation. They browsed on shrubs and trees rather than grazing, filling a niche similar to deer or antelope elsewhere. Megalania, a giant monitor lizard, was the largest venomous vertebrate ever to exist. Reaching over 5 meters in length and weighing up to 600 kilograms, Megalania hunted large prey using ambush tactics, toxic saliva, and razor-sharp teeth. Like modern Komodo dragons, it probably inflicted deep wounds and tracked prey until venom and bacteria caused death from blood loss and infection. Evidence suggests Megalania occasionally attacked humans, though whether it regularly preyed on people or only opportunistically remains unclear. Thunderbirds, several species of enormous flightless birds called genyornis, roamed Australian grasslands until humans arrived. Standing over 2 meters tall and weighing up to 200 kilograms, these birds were herbivorous or omnivorous, using powerful beaks to crack seeds and crush vegetation. They couldn't fly but could run swiftly, filling a niche similar to ostriches or moas. Their eggs, larger than those of any living bird, have been found in ancient hearths, showing humans collected and cooked them. Giant wombats, echidnas the size of sheep, enormous python relatives, and massive terrestrial crocodiles added to Australia's megafaunal diversity. One species of land crocodile, quincana, had deep, laterally compressed skulls with blade-like teeth, suggesting it actively hunted rather than ambushed from water. These terrestrial crocodiles chased prey across land, a hunting strategy abandoned by modern crocodilians. Australia's megafauna faced unique environmental challenges. The continent was drying through the Ice Age, its interior becoming increasingly arid as global cooling reduced rainfall. Lakes that once dotted the landscape dried into salt pans. Rivers that flowed year-round became seasonal or disappeared. Vegetation communities shifted from forests to woodlands, to grasslands to desert. Species dependent on permanent water sources found their ranges shrinking. But Australia's megafauna had survived these changes for millions of years, adapting to increasing aridity through behavioural flexibility and physiological adaptations. What changed dramatically when humans arrived was predation pressure combined with habitat modification through fire. Aboriginal Australians used fire systematically to manage landscapes, burning vegetation to promote new growth, drive game, and maintain preferred habitats. This fire regime transformed Australian ecosystems from mosaic woodlands to more open grasslands and increased fire frequency beyond natural patterns. The combination of human hunting and anthropogenic fire may have pushed megafauna past critical thresholds. Species already stressed by climate change faced new mortality from hunting, especially of juveniles and reproductive age adults. Fire reduced vegetation diversity and created habitats less suitable for browsers and mixed feeders. Reproduction rates couldn't compensate for increased mortality. Populations fragmented into isolated pockets, reducing genetic diversity and making recovery impossible. Archaeological evidence shows humans definitely hunted some Australian megafauna. Butchered bones, stone tools found with fossils, and middens containing megafauna remains proof direct predation. But the extent of hunting versus climate impacts remains intensely debated. Unlike North America, where hundreds of kill sites document intensive megafauna hunting, Australian evidence is sparser and more ambiguous. What's certain is that within a few thousand years of human arrival, Australia lost over 85% of its megafauna, genera and species that had persisted for millions of years. By 40,000 years ago, most were gone. The marsupial lion disappeared. Diprotodon vanished. Giant kangaroos, thunderbirds, megalania, and dozens of others went extinct. Only smaller species survived, creating the distinctly impoverished megafauna community seen today, where the largest native land animal is the red kangaroo weighing around 90 kilograms. This transformation was the first megafaunal extinction wave of the late Quaternary, preceding similar events in the Americas and Madagascar by tens of thousands of years. It established a pattern that would repeat globally. Humans arrive in a region with naive megafauna. Extinctions follow within millennia. Ecosystems transform permanently. Australia's giants were the first casualties of humanity's global expansion, victims of a species that had evolved predatory skills in Africa and Eurasia, but entered isolated continents where prey animals had no evolutionary experience with human hunting tactics. The climate shifts. Nothing about the Ice Age was stable, not temperature, not rainfall, not vegetation, and certainly not the ice itself. The last glacial maximum represented a period when ice sheets reached maximum extent, but getting there involved wild fluctuations, abrupt shifts, and climate changes so rapid that ecosystems collapsed within human lifetimes. Ice cores from Greenland preserve annual layers going back over 100,000 years, creating detailed climate records that reveal a terrifying truth. The Ice Age didn't end gradually, but lurched between frozen and warm states with shocking speed, driven by mechanisms scientists still don't fully understand. These shifts killed indiscriminately, transforming entire landscapes and forcing every species to adapt, migrate, or perish. The most dramatic of these events were Dansgaard-Oeschger cycles, abrupt warming episodes that occurred repeatedly throughout the Ice Age. Greenland ice cores show that temperatures could spike by 10 degrees Celsius or more within decades, sometimes within just a few years. These weren't gradual transitions. They were climate earthquakes that fundamentally reorganized atmospheric and oceanic circulation. Winters became milder. Precipitation patterns shifted. Vegetation zones moved hundreds of kilometers, and ecosystems that had stabilized over thousands of years faced sudden chaos. What caused these abrupt shifts? The leading theory involves changes in the Atlantic meridional overturning circulation, the system of ocean currents that moves warm water north and cold water south, regulating global heat distribution. When fresh water from melting glaciers flooded into the North Atlantic, it disrupted this circulation, reducing heat transport to the north and causing rapid cooling. When circulation resumed, warmth returned quickly. This on-off switching created the saw-tooth climate pattern visible in ice cores, long, cold periods punctuated by brief, intense warming episodes. Heinrich events were even more catastrophic, massive pulses of icebergs breaking off from ice sheets and flooding into the North Atlantic. These events released so much fresh water that they disrupted ocean circulation completely, plunging regions around the Atlantic into cold that killed vegetation, froze lakes, and caused widespread mortality. Evidence of Heinrich events appears as layers of ice-rafted debris in ocean sediments, rocks and soil carried by icebergs and dropped as they melted, creating distinctive geological signatures. The Younger Dryas was the most famous climate shift, a return to near glacial conditions just as the world was warming out of the Ice Age. Around 12,800 years ago, temperatures across the Northern Hemisphere plummeted, glaciers advanced, and ecosystems that had begun transitioning toward warmer conditions were suddenly frozen again. This cold snap lasted over 1,000 years before ending as abruptly as it began. The cause remains debated, possibly a massive freshwater pulse from glacial Lake Agassiz flooding into the Atlantic, possibly a comet impact that triggered cooling, possibly changes in solar activity or atmospheric circulation. Whatever the cause, the Younger Dryas had profound effects on human societies and ecosystems. In the Middle East, human populations that had begun experimenting with agriculture faced crop failures and resource scarcity, possibly accelerating the transition from hunter-gatherer to farming societies. In Europe, forests retreated and megafauna that had survived earlier climate shifts finally disappeared. In North America, the Clovis culture, characterized by distinctive spear points and big game hunting, gave way to different traditions, adapted to changing conditions. Climate shifts also occurred on regional scales, creating patchworks of changing conditions. While the North Atlantic region experienced abrupt cooling during Heinrich events, tropical regions saw shifts in monsoon patterns, affecting rainfall from Africa to Asia. The Australian monsoon weakened during cold periods, increasing aridity. South American rainfall patterns shifted, causing forests to fragment and grasslands to expand or contract. These regional changes didn't necessarily align with global patterns, creating complex ecological pressures that varied geographically. Vegetation responded rapidly to climate shifts. Pollen cores from lakes and bogs show plant communities could reorganize within decades, with cold-adapted species replacing temperate ones during cooling episodes and vice versa during warming. Tree lines moved up and down mountains, forests expanded and contracted, and plant species migrated hundreds of kilometers, tracking suitable climates. These shifts weren't orderly marches. They were chaotic reassemblies where species that had coexisted for millennia suddenly couldn't survive together, and new combinations formed. Animals responded by migrating, adapting, or going extinct. Species with broad environmental tolerances, like wolves and foxes, tracked shifting prey populations. Specialists with narrow habitat requirements faced extinction if their preferred environments disappeared faster than they could migrate. Large herbivores that needed specific vegetation types found themselves in shrinking refuges. Predators that depended on specific prey faced starvation when those prey populations crashed. Humans responded with characteristic flexibility, adjusting hunting strategies, exploiting new resources, and migrating to track favourable conditions. But even humans faced mortality during the worst climate shifts. Archaeological evidence shows population crashes, abandoned settlements, and cultural discontinuities associated with rapid climate changes. The flexibility that made humans successful wasn't unlimited. Severe shifts caused suffering, mortality, and sometimes local extinctions of human populations. The end of the Ice Age, around 11,700 years ago, wasn't gradual. After the Younger Dryas ended, temperatures rose sharply, ice sheets collapsed, and sea levels rose meters per century in some periods. This warming was more stable than previous shifts, allowing ecosystems to reorganize into relatively stable configurations that have persisted with modifications to the present. But the speed of change was still dramatic by geological standards. Within a few thousand years, ice sheets that had taken tens of thousands of years to build melted completely. Forests replaced tundra and grasslands, and sea levels drowned coastal plains where humans had lived for millennia. The Great Extinction. Within just a few thousand years, an eye blink in geological time, the megafauna that had defined Ice Age ecosystems vanished from most of Earth, erased so thoroughly that their existence would be doubted if not for fossils preserved in tar pits, caves, and permafrost. Mammoths, mastodons, giant ground sloths, saber-toothed cats, short-faced bears, woolly rhinoceroses, giant wombats, and dozens of other large mammal genera disappeared, leaving ecosystems impoverished and transformed. This wasn't a single event, but a rolling wave of extinctions that swept across continents as climate shifted and humans spread, culminating in the most severe loss of large animal diversity since the asteroid that killed the dinosaurs. The debate over what caused this catastrophe remains one of the most contentious in paleontology. The timeline is revealing. Australia's megafauna disappeared around 46,000 years ago, shortly after human arrival. Northern Eurasia lost most megafauna between 15 and 10,000 years ago as climates warmed. North America's extinctions clustered between 13 and 11,000 years ago, coinciding with rapid climate change and expansion of human populations. South America's megafauna vanished between 12 and 10,000 years ago. Madagascar lost its megafauna around 1,000 years ago when humans arrived. The pattern is unmistakable. Extinctions followed human arrival, often within a few thousand years. This timing has fueled the overkill hypothesis, the theory that human hunting directly caused megafaunal extinctions. Proponents point to several compelling arguments. First, humans were uniquely effective predators with sophisticated weapons, cooperative hunting strategies, and ability to drive prey off cliffs or into traps. Second, megafauna on continents lacking previous human presence, Australia, the Americas, Madagascar, had no instinctive fear of humans and fell victim rapidly. Third, the selective extinction of large animals while smaller species survived suggests a predator targeting size rather than climate, which would affect species indiscriminately. Fourth, computer models show that even modest hunting pressure, killing just a few % of adult females annually, could drive megafauna populations to extinction within centuries, given their slow reproduction rates. Archaeological evidence supports human predation. Kill sites across North America preserve mammoth and mastodon bones with stone tools and butchery marks. The Clovis culture, characterized by distinctive spear points, appears in the archaeological record just before megafaunal extinctions. Sites from Alaska to Chile show humans hunted horses, camels, ground sloths, and other now extinct animals. In Australia, some sites contain megafauna bones with butchery marks, though evidence is sparser than in the Americas. But the overkill hypothesis faces serious challenges. First, kill sites are relatively rare compared to the abundance of megafauna fossils, suggesting hunting wasn't ubiquitous. Second, climate change during the same period was dramatic, with temperatures rising, ice sheets collapsing, and vegetation communities reorganizing. Changes severe enough to stress even well-adapted species. Third, some megafauna survived initial human contact for thousands of years before going extinct, suggesting factors beyond immediate hunting pressure. Fourth, extinctions in northern Eurasia occurred later despite earlier human presence, arguing against simple overkill. The climate change hypothesis argues that warming at the end of the Ice Age fundamentally disrupted megafaunal habitats. As ice sheets melted, the mammoth steppe disappeared, replaced by forests in some areas and wet tundra in others. Neither habitat supported the productive grasslands megafauna depended on. Trees shaded out grasses, reducing forage quality and quantity. Wet tundra became boggy and difficult to traverse, trapping animals and reducing mobility. Vegetation communities that had persisted for tens of thousands of years reorganized into novel assemblages where familiar plant associations disappeared. These habitat changes would have stressed megafauna severely. Mammoths and rhinoceroses adapted for grazing found themselves in woodlands with browse instead of grass. Horses and bison faced shrinking grasslands. Ground sloths lost the open vegetation they browsed. As habitats fragmented, populations became isolated, reducing genetic diversity and making recovery from climate-driven mortality impossible. Reproduction rates, already slow in large mammals, couldn't compensate for increased adult mortality and juvenile deaths. The most likely explanation involves synergy between human hunting and climate change. Each factor alone might have been survivable, but combined, they were lethal. Climate change fragmented populations, reduced reproduction, and increased mortality. Human hunting added additional pressure, targeting reproductive age adults and preventing population recovery. Together, these pressures drove species past tipping points from which recovery was impossible. Evidence supports this synergistic model. Mammoths survived multiple previous climate shifts without extinction, suggesting climate alone wasn't sufficient. But previous warmings lacked human hunting pressure. Conversely, humans and megafauna coexisted in Africa, for hundreds of thousands of years without extinction, suggesting hunting alone wasn't sufficient when prey species had evolved defences against human tactics. Only when naive megafauna faced both climate stress and human hunting did extinctions occur. The ecological consequences were profound. With megafauna gone, ecosystems transformed. Grasslands vanished as large herbivores that maintained them through grazing and trampling disappeared. Forests expanded without elephant-sized browsers to control seedling growth. Nutrient cycling changed as dung from massive herbivores stopped fertilizing landscapes. Scavenger populations crashed without megafaunal carcasses. Predators that specialized on large prey went extinct, while generalist predators and smaller species survived. Humans also faced consequences. Big game hunting cultures collapsed as prey disappeared, forcing transitions to broader diets including smaller animals, fish, and plants. Some human populations declined or disappeared when specialized subsistence strategies became unviable. The relatively easy calories from hunting mammoths ended, requiring intensified foraging and eventually contributing to agricultural development as humans sought more reliable food sources. The extinctions also eliminated evolutionary potential. Mammoths, ground sloths, and other megafauna represented millions of years of evolutionary experimentation, unique adaptations, body plans, and ecological roles that can never be recreated. Their loss impoverished Earth's biodiversity permanently, removing charismatic species that shaped landscapes and inspired human cultures. Cave paintings from Europe to Australia show humans lived alongside and revered these animals, creating art that outlasted the creatures themselves. Today, those paintings are ghosts, images of a world that no longer exists, casualties of the most dramatic ecological transformation since the age of dinosaurs ended.